So, today we will consider thermally fully developed laminar slug flow with uniform wall heat flux condition. So, today we will consider two different types of channel. First we will consider flow through parallel plates channel, and next we will consider flow through circular pipe. As you know that it is thermally fully developed flow. So, obviously, the non-dimensional temperature we have defined as T w minus T divided by T w minus T m. So, it will not vary in axial direction, and we will consider uniform wall heat flux, and you know that in this particular case del T by del x will be constant. So, you can see that for Prandtl number much less than 1, where Prandtl number is defined as nu by alpha, right. Prandtl number is nu by alpha, where nu is the momentum diffusivity, alpha is the thermal diffusivity. So, for Prandtl number much less than 1, the thermal diffusivity is more than the momentum diffusivity. The temperature profiles develop more rapidly than the velocity profile near to the inlet. In such a situation, it is appropriate to assume axial velocity to be uniform across the cross section. However, results developed under such assumption cannot be extended too far downstream, and this axial velocity when we consider as uniform, that is known as slug flow. So, the assumptions for today's class will consider two dimensional, steady, incompressible, laminar slug flow with constant properties. So, slug flow means u is constant, okay, u is constant, and in this particular case we will take u is equal to u m. Okay. So, you can see this is the channel with two infinite parallel plates. X is the axial direction, y is measured from the central line, q double prime w is the constant heat flux applied to both the walls. These two plates are separated by distance 2h, and you have uniform velocity because it is slug flow. Obviously, if it is uniform, then your v velocity will be also 0. So, v is also 0, v is the velocity in y direction. Thermally fully developed flow. So, del phi by del x will be 0, okay, where phi is the non-dimensional temperature, T w minus T divided by T w minus T m. Uniform wall heat flux condition. So, q double prime w is constant. Negligible viscous heat dissipation. So, phi is 0 and no internal heat generation. So, q triple prime is 0. So, for this particular case, let us write the energy equation in general for steady two dimensional situation. So, energy equation u del T by del x plus v del T by del y is equal to alpha into del 2 T by del x square plus del 2 T by del y square, okay, neglecting the viscous dissipation and heat generation. So, now for uniform wall heat flux boundary condition, you know the del T by del x, right, we have already derived. So, for uniform wall heat flux, okay, del T by del x is equal to dTm by dx, and that is equal to q double prime w p by m dot c p, and you can see that q double prime w is constant, p is the perimeter. If you have a constant cross sectional channel, then p is also constant, m dot is constant, c p is constant. So, this will be constant. Hence, del 2 T by del x square will be 0, because del T by del x is constant. So, del 2 T by del x square 0. So, for this particular case, you can see that your axial heat conduction is 0. So, for slug flow you can put u is equal to um and v is equal to 0. So, u is equal to um and v is equal to 0. So, all these if you put it in this energy equation, what you will get? So, you will get um. So, del T by del x, you can write dTm by dx, okay. Then v is 0, okay. So, v is 0, so this term will get 0, del 2 t by del x square is 0. So, you will write alpha into del 2 t by del y square, okay. So, you can write it as del 2 t by del y square is equal to u m by alpha into dTm by dx. So, we have the equation del 2 t by del y square is equal to u m by alpha dTm by dx. So, this is constant, okay. So, what you can do now, you can integrate it. So, you can write del t by del y is equal to u m by alpha dTm by dx y plus integration constant C1, and it may be function of x, because t is function of x and y, and another time if you integrate, then you can write t which is function of x and y, you can write u m by 2 alpha dTm by dx into y square plus C1 y plus C2 y, C2 function of x. So, now let us discuss about the boundary conditions. So, at central line you have a finite temperature, and you can see in this particular case about the central line you have geometrical symmetry, because both walls are at distance h from the central line. At the same time we have thermal boundary condition which is symmetric, because in both walls we have uniform wall heat flux boundary condition. So, you can see that it is geometrically and thermally symmetric. So, at y is equal to 0 at the central line you will have either maximum or minimum temperature. Hence, you can write del T by del y at y is equal to 0, which is your central line, will be 0. So, one boundary condition is that y is equal to 0, okay. You have del T by del y is equal to 0, okay. And another boundary condition at y is equal to h, okay, you can have temperature T is equal to T w, which is function of x. So, we are assuming that you have wall temperature T w which varies in axial direction, and that is T is equal to T w at y is equal to h. So, now if you put at y is equal to 0 del T by del y as 0, then you can see from this equation, okay, this equation you can see that C1 will be 0, and at y is equal to h, if you put T is equal to T w, then you can see that it will be T w which is function of x, it will be u m by 2 alpha dTm by dx h square plus C2. So, hence your C2 will be, which is function of x, because T w is function of x. So, it will be T w minus u m by 2 alpha dTm by dx into h square. So, now let us simplify this u m by 2 alpha dTm by dx h square term. Okay. So, let us apply the boundary condition at r is equal to r 0, you have a uniform wall heat flux q double prime w is equal to constant. Okay. So, obviously you can write at y is equal to h, okay, at y is equal to h. Now, k into del T by del y, okay, at y is equal to h. So, it is y is equal to 0 will be q double prime w. So, you can see your y is in the positive upward direction, right. So, but q double prime w is the negative y direction, okay, what we considered in this diagram. So, obviously, your in negative y direction the heat conduction will be k del T by del y at y is equal to h, and that is equal to q double prime w. So, from here now you can see del T by del y from this equation C 1 is 0. So, del T by del y if you put, then you will get k you just divide in the right hand side. So, you will get u m by alpha dTm by dx into h will be q double prime w by k, okay. And hence you can write u m by alpha dTm by dx, okay. So, this you can write q double prime w by k h, okay. So, now this term, so you can see u m by 2 alpha dTm by dx, that term you can write with q double prime w by k h, okay. This we can also similar way we can derive straightforward from this expression of dTm by dx, because you know that dTm by dx for this uniform heat flux boundary condition is q double prime w p by m dot C p. Okay. So, this is constant, already you have written. So, now you tell me what is P? Perimeter. Okay. So, this perimeter is the heat transfer area on the wall. Okay. So, per unit width if you consider, then it will be 2, or if you W is the width if you consider, then on the upper wall it is W, bottom wall it is W, then 2 W, or per unit width if you consider, then 2 into 1. And what is the flow area? Flow area is the distance between two parallel plates is 2 h. So, 2 h into W, or per unit width if you consider, then it will be 2 h. So, you can write q double prime W. So, I am write just 2 into 1, okay, per unit width I am writing, and m dot is rho u m, okay, rho u m, and area is I told that it is 2 h into per unit width into C p. Okay. So, now if you see this term u m by alpha dTm by dx, if you write, so it will be u m, alpha is k by rho C p, dTm by dx is this 2 will get cancelled. Okay. So, you can see that you can write q double prime w divided by rho u m h into C p. So, now rho C p, this will get cancelled, u m will get cancelled. So, finally, you will get as q double prime w by k h. Okay. So, you can see from here also we found u m alpha dTm by dx as q double prime w by k h, and similarly from directly this expression also same we got q double prime w by k h. Now, you write the final temperature distribution putting the value of C 2. So, if you write the temperature distribution, so C 1 is 0, C 2 is this. So, it will be T x y. So, u m by alpha dTm by dx is q double prime w by k h. So, it will be q double prime w by twice k h into y square plus C 2. C 2 is T w x, okay, T w which is function of x, minus again u m by alpha dTm by dx, we will put q double prime w by twice k h, okay, into h square. Okay. So, now you can see, so if you rearrange it, so we will rearrange it as T x y, okay, is equal to T w, okay. Then I will write as minus, I will take h squared. So, this h, so this one will be h. So, you can write q double prime w into h by 2 k. Okay. So, this I am taking common. So, you will get 1 minus, so there h square will be there. So, y square by h square. Okay. So, this is the temperature distribution. This temperature distribution also we can write in terms of the central line temperature. So, what will be central line temperature? At y is equal to 0, you will get the central line temperature. So, if it is so, so you will get central line temperature T c at y is equal to 0, right. So, y is equal to 0, you will get the central line temperature. So, if you put y is equal to 0 in this equation, you can find the central line temperature T c, which is function of x, as T w x minus q double prime w h by twice k. So, you can see that if you can write T w x minus T c x is q double prime w h by twice k. Okay. And if you put it here, and you can write the temperature distribution in terms of the central line temperature. Okay. So, it will be T w minus T x y divided by T w x minus central line temperature T c is equal to. So, you can see you can write 1 minus y square by square. Okay. So, to calculate the heat transfer coefficient, we need to find the mean temperature, because we will define the Nusselt number or the heat transfer coefficient based on the difference between world temperature and the mean temperature. So, let us calculate the mean temperature now. You know that mean temperature you can calculate as T m is equal to 1 by m dot, okay, integral over flow area rho u t dA. Okay. So, in this particular case, as we consider the slug flow, so u m is constant. Okay. So, you can write 1 by rho u m into A, here also rho u m t into dA. So, what will be the flow area in this particular case? So, particular case per unit width your flow area is 2 h, okay. And what is your dA? dA is dy, okay. So, dy into 1 per unit width, dA is dy, okay. So, dy into 1 and this is also into 1. So, per unit width we are defining. So, this rho u m will cancel out. So, you can write T m as, so 1 by area 2 h, okay, minus h to h, then your temperature distribution. What is your temperature distribution? So, that we have written as T w, okay, minus q double prime w h by twice k into 1 minus y square by h square, okay, into dA. dA is dy. Okay. So, now this integral minus h to h we will write as 0 to h. So, 2 you can take it outside. So, 2 h. So, it will be 0 to h. Okay. So, you can write T w minus q double prime w h by twice k into 1 minus y square by h square into dy. Okay. So, you can write now 1 by h. Okay. So, first term, so it will be just integral dy 0 to h. So, it will be t w into h. Okay. Then minus q double prime w h by twice k. Okay. So, now you can see this one. So, this one will be dy, integral dy. So, it will be y, and y if you put the values 0 to h. So, it will be h only, and now this will be y square. So, y cube by 3. So, h cube by 3. Okay. So, after putting the limits I am writing this. Okay. So, 0 to h. So, 0 will be 0, and at h I am just writing after integrating y cube by 3 h square. So, y cube, if you put y is equal to h. So, it will be h cube. So, now if you multiply with 1 by h. So, it will be t w minus, so it will be q double prime w. So, this h and this h will get cancelled. So, by 2 k, and here h if you take outside. So, it will be 1 minus 1 by 3. So, it will be 2 by 3. Okay. So, you will get finally T m as T w x. T m is also function of x. Okay, minus q double prime w h by 3 k. Okay. So, the difference between the wall temperature and the mean temperature you can write as q double prime w h by 3 k. Okay. So, now we can calculate the heat transfer coefficient. So, what is your heat transfer coefficient? Heat transfer coefficient is q double prime w divided by T w minus T m, that we got that equating the Fourier's law and the Newton's law of cooling. So, you can write H as q double prime w divided by T w minus T m, okay, and we have seen that T w minus T m, okay, is q double prime w h by 3 k. Okay. So, now if you put it here, so you are going to get h is equal to q double prime w divided by, so this if you put it here, so you will get q double prime w h into 3 k. Okay. So, you can write H in terms of thermal conductivity of the fluid and the distance from the center line to the wall 3 k by h. So, now you will be able to calculate the Nusselt number. Nusselt number you can calculate based on the hydraulic diameter. So, what is the hydraulic diameter of this particular case? So, you have a two parallel plates separated by distance 2 h. Okay. So, your hydraulic diameter in this particular case, so hydraulic diameter will be dH as 4 into flow area divided by the perimeter. So, what will be that? 4 into flow area is per unit width is 2 h, okay, divided by perimeter. So, per unit width it is 2. So, it will be 4 h. Okay. So, we will define the Nusselt number based on the hydraulic diameter, that is 4 h, and the difference between the mean temperature, difference between the wall temperature and mean temperature. So, Nusselt number now we will define as h into 4 h by k, and now h is 3 k by h, and you have 4 h by k. So, hence you can see that it will be 12. Okay. So, Nusselt number for this slug flow and thermally fully developed flow inside the parallel plates channel is 12. So, it is based on 4H, okay, hydraulic diameter based on 4H. Okay. Next, let us consider thermally fully developed laminar slug flow through circular pipe with uniform wall heat flux condition. So, the assumptions will take that it is axisymmetric. Axisymmetric means circumferential variation is 0 and velocity is also 0. So, what is axisymmetric? Axisymmetric means the circumferential variation of any quantity is 0 and in that direction velocity is also 0. Okay. And you can see in this particular case geometrically and thermally, because you have uniform wall heat flux boundary condition. So, it is axisymmetric. So, you can write for axisymmetric steady incompressible laminar slug flow with constant properties. So, u is equal to u m, okay, and v is equal to 0. So, you can see x is the axial direction, r is the radial direction and it is measured from the center line. At r is equal to r naught, your heat flux q double prime w is constant, okay, and you have a slug flow. So, your velocity profile is constant and that is equal to u m. So, thermally fully developed flow. So, del phi by del x will be 0, uniform wall heat flux condition. So, q double prime w is equal to constant, negligible viscous heat dissipation. So, phi is equal to 0 and no internal heat generation, q triple prime is equal to 0. So, now let us write the energy equation in cylindrical coordinate for axisymmetric and steady incompressible and laminar flow. So, energy equation you can write in cylindrical coordinate as u del t by del x plus v del t by del r is equal to alpha del 2 t by del x square plus 1 by r del of del r into r del t by del r. Okay. So, now for constant heat flux boundary condition we can write del t by del x is equal to constant and hence del 2 t by del x square is equal to 0. So, for uniform wall heat flux del t by del x is equal to dTm by dx is equal to q triple prime w p by m dot Cp is equal to constant. Hence, your axial heat conduction del 2 t by del x square is equal to 0. Okay. And for slug flow you can see V is equal to also 0. Okay. So, if you put this in this energy equation, so you will get u is equal to also u m. So, you can write u m, okay, into del t by del x. So, you can write as q double prime w p by m dot C p. Okay. This alpha will take in the left hand side. So, alpha and this will be r, okay, is equal to we can write right hand side as del of del r, r into del t by del r. Okay. So, now in left hand side you put the values of p, perimeter, m dot, mass flow rate, okay, and alpha k by rho Cp. So, if you put it and simplify it, what you will get? So, you can see, so you can write u m by alpha q double prime w p by m dot Cp. Okay. So, it will be u m k by rho Cp, okay, q double prime w p. So, for this particular case it is twice pi r naught divided by mass flow rate, it will be rho u m into area pi r naught square into C p. So, if you simplify it, so pi and u m will get cancelled. So, you will get finally this equal to, so twice q double prime w by k r naught. Okay. So, if you put it here, so you will get del of del r into r del t by del r is equal to twice q double prime w by k r naught, and one r is here. So, into r. So, now this equation you can integrate twice and you can find the temperature distribution for thermally fully developed laminar sag flow through circular pipe with applying two boundary conditions. At r is equal to 0, you have T is finite, and at r is equal to r naught, you have wall temperature T w, right. So, that is why we have started with the simple problem considering the slug flow, because your right hand side is becoming constant. So, it is easy to integrate and find the temperature distribution and the heat transfer coefficient. So, now let us find the temperature distribution. So, you have del of del r, r del t by del r is equal to twice q double prime w by k r naught into r. So, if you integrate it first, then you will get r del t by del r will be twice q double prime w by k r naught into r square by 2 plus C 1, okay, which may be function of x. Then if you divide by r, then you will get, so these 2 will get cancelled. So, you will write 2 double prime w okay. So, r you are dividing, okay. So, it will be just r plus C 1 by r. Now, if you integrate again, so you will get t, which is function of x r. So, you can write q double prime w by k r naught r square by 2 plus C 1 ln r plus C 2, which may be also function of x. So, what are the boundary conditions? So, one boundary condition is that at r is equal to 0, okay, T is finite, and another boundary condition you can write at r is equal to r naught, you have a wall temperature T w. So, boundary conditions at r is equal to 0, you have T is finite, okay, and also you can see that geometrically and thermally it is symmetric. So, del T by del r also you can write 0. So, you can see if r is equal to 0, if you put, so obviously C 1 must be 0, okay. So, because this is your 0, so T is finite, so this cannot be infinite. So, C 1 must be 0. So, C 1 is 0 and r is equal to r naught, you have wall temperature T w. So, if you put it that T w, which is function of x, q double prime w by k r naught r naught square by 2 plus C 2. Okay. So, you can see C 2 will be your T w minus q double prime w by k r naught, or you can write twice k into r naught. Okay. So, now these constants you put in the temperature profile and find the temperature distribution. So, you can write T, so it will be q double prime w by k r naught r square by 2 plus C 2 q double prime w r naught by twice k. Okay. So, this you can write as T x r is equal to T w x minus q double prime w r naught by 2 k, you take common. So, you will get 1 minus r square by r naught square. Okay. So, which is your temperature distribution. Now, if you write in terms of the center line temperature, then you put at r is equal to 0, T is equal to T c. So, at r is equal to 0, your central line temperature will be T c, which is function of x T w x, okay, minus q double prime w r naught by twice k. Okay. So, if you put it here, so if you rearrange, you are going to get this temperature profile T w x minus T c divided by T w x minus T x r divided by T w x minus T c x, you can write 1 minus r square by r naught square. Okay. So, now next we need to find the mean temperature to find the heat transfer coefficient. So, you can write T m, okay, as 1 by m dot integral over area rho u T dA. Okay. So, now what is m dot? M dot is your 1 by rho u m, okay, and what is the area? Flow area is pi r naught square, and this you can write rho u is constant slug flow. So, it is u m and the temperature distribution. So, what is the temperature distribution? So, you wrote temperature distribution as T w, okay, minus q double prime w r naught by twice k 1 minus r square by r naught square. Okay. And what is dA? So, you can see. So, if you consider one elemental flow area at a distance r of distance dr, then this is your flow area, and that you have to find what is the dA. So, what is the dA in this case? So, it is perimeter is twice pi r into distance dr. So, that is the flow area, twice pi r dr. Okay. So, that you can write here. So, this is your twice pi r dr. Okay. So, now u m rho this pi will get cancelled. So, and now you integrate it from 0 to r naught. Okay. So, what you will get? So, you can write 2 by r naught square, okay, 2 by r naught square, and you can write 0 to r naught, okay, and this r you multiply with T w, okay, into r minus q double prime w r naught by twice k into r minus r cube by r naught square, okay, into dr. So, now you integrate it. So, twice you can integrate it 2 by r naught square. So, what will be this one? It will be T w into r naught square by 2, right. The integration will be r square by 2. So, if you put the limit, so it will be r naught square by 2 minus q double prime w r naught by twice k, okay, and this if you put, what you will get? It will be r square by 2. So, it will be r naught square by 2, it will be r to the power 4 by 4. So, if you put the limit, it will be r naught to the power 4 by 4 r naught square. Okay. So, if you simplify it, so if you multiply with this, so it will be T w minus, so if you multiply 2 by r naught square q naught w by r naught by twice k, and if you subtract it, so it will be r naught square by 4, okay, because r naught square by 2 minus r naught square by 4. So, r naught square half minus 1 by 4, so it will be 1 by 4. So, now you can write it as, so these 2 r naught square you can cancel, and you can write this as T w minus q double prime w r naught by 4 k. Okay. So, now you can write the temperature difference T w x minus Tmx as q double prime w r naught by 4k. Okay. So, now you find the heat transfer coefficient. Okay. Heat transfer coefficient you can write as q double prime w by T w minus T m. So, heat transfer coefficient. So, H you can write q double prime w by T w minus T m. Okay. So, in last slide we have found T w minus T m, okay, as q double prime w r naught by 4k. Okay. So, this H will be then q naught w divided by, so this temperature difference you can write as divided by q naught w r naught and into 4k. Okay. So, this you cancel, then you will get H, which is your heat transfer coefficient, as 4k by r naught. Now, we will find the Nusselt number, okay, based on the hydraulic diameter, and for a pipe hydraulic diameter is just diameter of the pipe. So, it is 2 r naught. So, we will find the Nusselt number based on 2 r naught. So, Nusselt number, okay, based on diameter. So, diameter is just 2 r naught. Okay. This is your hydraulic diameter. So, Nusselt number based on diameter you can write H twice r naught by k. Okay. So, Nusselt number based on diameter. So, H is 4k by r naught into twice r naught by k. So, you can see, so this r naught k k you can cancel. So, you will find Nusselt number based on diameter, and the difference between the wall temperature and mean temperature will be 8. Okay. Later we will calculate this thermally fully developed and hydrodynamically fully developed condition with uniform wall heat flux for this condition, okay, for pipe flow, and Nusselt number you will find it as, so hydrodynamically and thermally fully developed. Thermally fully developed flow through pipe, okay, with uniform wall heat flux. This will calculate. Okay. So, we will calculate later. So, you can calculate Nusselt number based on diameter, it will be 4.363. Okay. You will get Nusselt number as 4.363. So, obviously, you can see that as you have uniform velocity, obviously near to the wall you have more velocity, hence you will get more heat transfer, and that you can see for Nusselt number as 8. And also you notice that your Nusselt number is constant for this fully developed flow. So, let me summarize. So, today we have considered thermally fully developed laminar slug flow, okay, in two different types of channels. One is parallel plate channel and one is circular pipe, and we considered uniform wall heat flux boundary condition. For both the cases we calculated the temperature distribution first. You can see this is the temperature distribution for parallel plate channel, okay, and for pipe this is the temperature distribution. Here T is function of x and r, and in this particular case T is function of x and y. Then we calculated the mean temperature in terms of the wall temperature, because wall temperature is also varying. So, you can see for parallel plate channel this is the mean temperature variation, and for pipe flow this is the mean temperature variation. once we calculated the mean temperature, then we can calculate the difference between wall temperature and mean temperature, and from there we calculated the heat transfer coefficient. Okay. And this is the heat transfer coefficient for parallel plate channel 3 K by H, and for pipe flow it is 4 K by R naught. Then we calculated the Nusselt number based on the hydraulic diameter and the temperature difference between the wall temperature and the mean temperature, and we have found for this parallel plate channel Nusselt number based on hydraulic diameter as 12, and for pipe flow based on the diameter of the pipe as 8. And we have also discussed that if you consider the hydrodynamically fully developed flow, then obviously velocity will vary from u is equal to 0 at the wall to r is equal to 0 maximum velocity, and hence you will get less heat transfer in fully developed flow. Here we consider slug flow as your velocity is uniform and constant, hence we got higher heat transfer for this pipe flow. So, that is 8 we have shown, and in the case of fully developed hydrodynamically fully developed flow it is 4.36. Thank you.